Okay, hi, it's Eli again. In today's lesson, we're going to be going over U substitutions. So this is a method that we use when we evaluate integrals that help us evaluate integrals. Some integrals can't be evaluated without this technique. So say we have an integral of this form. We have like some function g of x times a function h of x dx. So there may be some substitution that we use. We may be able to set g of x or h of x to be some other variable, and that might help us evaluate this integral. That's the whole point of a u substitution. So let's just take, for example, g of x. Say we set u of x to equal g of x, and we'll just call that u. You don't have to call it u of x. So this is just for example. Let's see what happens. So now we have to write this whole integral in terms of u if we want to make this substitution, because we can't have u dx. That doesn't make any sense. Dx is a small piece along the x-axis, but now our integral is over the u-axis. So we have to change this. So the way we do that is using derivative. So we're going to take a derivative of u. So what's du dx? Well, looking at this equation 1, that's just g prime of x. Okay, so now we can think of this derivative as a fraction, actually, if you're a physicist, not a mathematician. So we can solve for dx, and then we can just plug that back in right here, and then we're pretty much done. So let's just solve for dx. Just multiply by dx here, and then divide by g prime of x, and we get dx equals du over g prime of x. Call this equation star. Okay, now let's see what happens when we plug this back into this integral, 2. So 2 becomes g of x is now u, h of x stays, and dx is du over g prime of x. I'll just write this g prime of x over this h of x. So if we made a good u substitution, this h of x over g prime of x should cancel. Again, like I said before, we can't have any x's in our integral. If there are x's after, that means we didn't make the right u substitution, or maybe u substitution doesn't work here. That's pretty much all you need to know. So now let's just do some examples. So let's say we have the integral of 1 over x ln x dx. And first I should preface, there are maybe some rules that might help you. First, we never make the substitution u equals x. This is a useless substitution. You're just redefining x to be u. It doesn't do anything for us. And 2, we usually set u to be the more complicated function. That's just kind of a general rule of thumb. Might not always work, but that might help you out. So for this integral, I'm just going to do that. I'm going to say that ln x is the more complicated function. I'm going to set u equals ln x. And plus, I don't want to set u equals x. I could have set u equals 1 over x, but that wouldn't actually help. And maybe that's something you guys can try. So now let's take a derivative of u. Du dx equals 1 over x, right? That's our g prime of x. And now use this equation star, solve for dx, or whatever. Dx equals x du. And if we look at this equation, this is du over g prime of x, because 1 over x is x. Easy stuff. So now let's sub back into our integral, right? We're going to leave this 1 over x alone. We didn't make any u substitution for it. We're going to make ln x equal u, and dx is x du. And would you look at that? Those x's, that 1 over x cancels with x. So we know we made a good u substitution. And so our integral over u is u du. And so now this is a very easy integral to do. It's u squared over 2 plus c And we have one more job, and it's the easiest job of the world, and that's just put back in ln x for u, because we want the answer to the integral of 1 over x ln x dx, not the answer of the integral of u du. So putting back in ln x, we get ln x squared over 2 plus c. And remember this plus c, it's important. And that's it. That's our answer. Let's do one more now. And this one I like because it shows you that sometimes you got to make more than one u substitution in a single problem. Let's say we have this integral, x squared times the root of x cubed plus 4. We could actually do this all in one step. Maybe we'll do it 2 ways. So the way I would do this is I would set u to be x cubed. And why? Because I see this x squared out here, and I know that the derivative of x cubed is like 3x squared or something. So something's going to happen. Sorry, there's a dx here. So we'll set u equals x cubed. And so, again, plugging into our formula star, we get dx equals du over g prime of u, which is 3x squared, like I said. Right? Plug it into the formula. We're going to get x squared times root u plus 4, and dx is du over 3x squared. So the x squareds are going to cancel, but we're going to have to keep this 1/3. That's what's telling us that we made a u substitution, because it did change. We have to add this 1/3. So it's 1/3 root u plus 4 du. So now we need to make one more u substitution, because I don't know what the antiderivative of root u plus 4 is, but I know the antiderivative of root u. So how do I make this now just a root u? How do I get rid of this 4? I make another u substitution. I'll call it a w substitution now. So I'll set w equals u plus 4. And now when we try to find dw, we're going to notice something very interesting. dw equals du, because this is a constant 4. When we take a derivative, it just goes away. Right? So then our final integral is just 1/3 root integral of root w dw. And that's easy. That one you can do by just make this root w equals w to the 1/2. Use the power law of integrals. Same thing as integrating x squared, just a different exponent. So I'll show you quickly how we could have just done this in one step. Because the 4 is just a constant, we could have just done this. We could have had, let's see, the essential integral of x squared root x cubed plus 4 dx. Now let's go straight to the w. Let's set w equals x cubed plus 4. What's dw? dw is 3x dw dx, 3x squared dx, because this 4 goes away. And so we would get the integral of 1/3 root w dw, which is the exact equation we wanted. So that question's done. So thanks for listening. Remember to comment anything that you want me to show you, and hope you learned something.